I would like to tell you a little bit about this recent joint work with Patrick Lopez-Cupampo, who I believe is in the audience, and then also Dimitri Stepanov. So the paper is on the archive, and the title is Local Tropicalizations of Splice-type Surface Singularities. So it's fitting that I'm giving this talk here because we first started thinking about this during research in Paris in Lumini a while back, and this is sort of one part of a long-term project aiming at proving a conjecture about Milnor, the topology of Milnor fibers of splice-type surface singularities. And Patrick gave a series of lectures in the summer school of this semester, and I think talking about the logarithmic aspect of the project. So I'm going to talk about the tropical aspect today. So if you attended those talks, you might think of my talk as a sort of complementary to Patrick's lectures. Okay. So let's get started. So first of all, I want to tell you what these splice-type surface singularities are. So you might think of them as generalizations of Brice-Kern complete intersections. This includes AN, E6, and E7 singularities in the classification by Duval. So my input is going to be a graph, which I'm going to call a splice-type diagram. It's going to have two additional properties that we'll discuss in a minute. But first, let's focus on the graph. So as a graph, we're going to have a tree that has no valency 2 vertices. So if there's any valency 2 vertices, we can ignore them. And then I'm going to divide the vertices of my graph into two types. I'm going to call the vertices nodes if their valency is at least 1. And I'm going to call them leaves if the vertices have valency 1. So if you think about the tree, the leaves of the tree are sort of end nodes of my graph. And then this is not just a graph, but it's equipped with positive integer weights around every node. So for every edge leaving a node, I'm going to have a weight on that edge next to my node B. So that's the definition of the splice-type diagram. And the two additional properties I have to impose are, one is going to be the edge determinant condition. And it's going to be required for every edge in my graph node joining two nodes. So what's this determinant condition? Well, if you fix two nodes, U and B, you're going to have weights surrounding U and weights surrounding V. And I'm going to call the determinant of this edge joining U and V. It's going to be the product of these two weights, P and Q. And I have to subtract from that the product of all the other weights surrounding U and V without including P and Q. So I'm going to take P times Q minus the product of the A's times the product of the B's. And that has to be, I'm going to require this to be a positive integer. We'll see an example in a minute. Then the second property I have to impose is the so-called semigroup condition. And this condition is going to be required for every pair of node and an edge adjacent to that node. So I'm going to build a semigroup. And so the semigroup is going to be constructed from generators. And these generators are going to be what we call the linking numbers of the vertices. If you give me two vertices, V and W, I'm going to refine the linking number between them as a product of all weights adjacent to, but not on the path joining V and W. So in the example here for the linking number, maybe I'll just write it down here. In the example, we have the linking number of U and V. In this case, it's going to be the product of the A's times the product of the B's. So in this case, there's a unique path joining U and V, and I have to ignore the two weights on the path from U to V. And then I'm going to define the quantity dV, which I can think of the linking number of the vertex V with itself. And that's just going to be the product of all weights around V. So in my example here, the dV is going to be Q times V1 times all the way up to V sub T. Okay? So I have these quantities, and the semigroup condition is going to require, or that the quantity dv, the linking number of v with itself, has to be in the semigroup generated by all the linking numbers between the vertex v and all the leaves that are in the path, all the leaves of the splice diagram that are sort of viewed in the direction of E from B, in the direction of E from the vertex V. So in this case, for example, I will take, if I want to compute the quantity, the semigroup condition on this node, I will have to consider only leaves here if the edge I'm looking at is the edge joining U and V. So I'm only going to look in the direction of my edge, and I'm going to consider all leaves in that direction. So that's going to give me this semigroup condition. As you can see, the V and the E are featured in the semigroup. Okay, so let's do an example. So two examples, excuse me. So again, the first the required property is this edge determinant condition. The second property is the semigroup condition. So let's see how what these look like in the examples. So the first one is Prieskorn complete intersection associated to the splice diagram with weights 2, 3, and 5. This is going to give me the E8 singularity that I was mentioning earlier in the first slide. So let's see what the quantities here are. So here, there's no determinant condition to impose because I don't have two nodes. I just have one node. So this condition is going to be vacuous. And then if I want to talk about the semigroup condition, I have just one node. So let's compute the dv here. So the dv is going to be the product of all weights adjacent to v. So this is 2 times 3 times 5. This is giving me 30. And then the semigroup condition requires me to consider the node together with the edges. So I'm going to have, in this case, 3 semigroup conditions associated to the pair V, the edge joining V to the first leaf. The second condition is going to be joining V and the edge joining V with the second leaf. And thirdly, I have the same node, and now the edge is the one joining V and lambda 3. So the condition I have to impose is 30 has to be in the semigroup generated by, now, for the first case, I have to consider leaves in the direction of this edge. Of course, leaves in the direction of this edge. Of course, there's just one. So the linking number in this case is going to be the product of all the weights joined in the adjacent to the path joining V and lambda 1, but not on the path. So that gives me 3 times 5, which is, of course, 15. And that is clearly valid. So 15 times 2 is 30. Similarly, for the second situation, I have to check if 30 is in the semigroup spanned by just one linking number. In this case, I have to consider the linking number for all leaves in the direction of lambda 2 that just leaves one leaf. And in this case, I have 10 as my generator. Of course, this is also clearly true. And finally, the third one is I have to check if 3 is in the semigroup generated by one linking number, the one between V and lambda 3, and the linking number in this case is 6. So it's also verified. Okay, so of course, as you see in this example, every time you have an edge joining a node with a leaf, the semigroup condition for those pairs of that node with that edges are going to be automatically true. So the observation here is that the semigroup condition is automatic for what we called for pairs that are a node and a node together with a leaf. Okay, so V here is a node and lambda is going to be a leaf. So that's good because then we have less things to check. Okay, so now let's look at the second example. So this is an example that is featured in a series of papers by Walter Neumann and Jonathan Wall. And so we're gonna borrow their example because it's simple enough that clarifies, simple yet illuminating enough that you can see the definitions in this example. So in this situation, we have, let's see. So now we're gonna have two types of weights, linking numbers to consider. We have two nodes. So in this case, we're gonna have dv is going to be, have to take the product of the weights adjacent to the node u. So this is 3 times 2 times 7. So that's 42. And then the second one is going to be 2 times 5 times 11, and that's 110. And so now that's going to be one of the things that we have to consider. The second property, well, in fact, the first property that we should consider was the edge determinant condition. So let's compute the determinant of the edge joining u and v. So in this case, I have to consider 7 times 11 minus, then I have the product of the exterior weights. So I have 2 times 3 times 2 times 5, and you compute, you get 77 minus 60, and that is clearly positive. Okay, so the edge determinant condition is valid. And now let's focus on the semi-group condition. As we said, we don't need to consider these 4 edges. So it's just one semi-group condition for each node in this case. So the first condition is with respect to the node u and the edge uv. So as we said, the d, sorry, I swapped the values here. This should be a u and this should be a v. I apologize for that. So u and v. So now we have to look at to check if 42 is in the semi-group generated by the linking numbers of u with respect to these two leaves, so lambda 3, and then u and lambda 4. In this case, we're going to get the linking number for u is going to be 2 times 3 times 2. So 2 times 3 times 2, and then we have 2 times 3 times 5. So that, of course, is 12 and 30. And of course, everything here is divisible by 6. So I can get rid of the 6 factor and check if it's true that 7 lies in the semi-group generated by 2 and 5. Of course, that is true. And in this case, it's true in a unique way. We can write 7 as exactly one positive combination of 2 and 5. In this case, all the scalars are going to be 1. Okay? And these scalars are something that we will remember for later in the talk. Okay, so now the second thing to check for the semi-group condition is the second linking number of v with itself is going to be 110, and I have to check if that's in the semi-group span by the linking number now of v with the other two leaves, so lambda 1 and lambda 2. Sorry, that should be a v here. And in this situation, we have the linking number is going to be now 2 times 5 times 3. That's going to give me the first of the two linking numbers. And then the second one is 2 times 5 times 3, times 2. This is going to be, now we're going to get 30 again and 20. Of course, again, everything is divisible by 10. So I can ignore the 10 factor, and I have to check if 11 is in the semi-group generated by 3 and 2. And of course, that is the case. But in this situation, we have two ways of realizing this statement. And so these two ways are going to give me later on two different types of splice systems. So the first situation is going to be 11 can be written as a combination of 3 and 2. And precisely, I can take 1 copy of 3 and 4 copies of 2. Or I can look at 11 and say, well, it's going to be obtained as adding 3 copies of 3, and then I have 1 copy of 2. So those are the two ways of writing this down. But at least I have to have one way to write every dV as in terms of the semigroup. Okay, so that's the situation. Now I'm going to tell you a little bit of history why these two conditions. So the first appearance of these splice diagrams were in the coprime setting. So that means that the weights that we consider around each node had to be pairwise coprime. So Siebermann introduced them in 1980 to encode integer homology spheres that are graph manifolds, and their construction is via plumbing. Now, in 85, Eisenberg and Neumann discussed the links of isolated complex surface singularities with integral homology spheres, and they realized them as coming from coprime splice diagrams that have this edge determinant condition. So that was necessary to get this type of result. And then in 83, Neumann showed that quasi-homogeneous normal complex surface singularities with rational homology sphere links have universal abelian covers that are Briscoe complete intersections. And then I think inspired by that, Neumann and Wall started thinking about what would happen if we don't have this coprime condition on the splice diagrams. So they develop a whole series of results, very, very illuminating, at least on my end. And so in the coprime splice diagram setting with integer homology spheres, then you can realize them as, or they yield complete, isolated complete intersection surface singularities if the semigroup condition is imposed. And the semigroup condition is gonna enable us to actually build systems of equations that will cut out these surface singularities as a complete intersection. And then, once you ignore this coprime condition, then you start thinking about rational homology sphere links, and then you can construct universal abelian covers. And they showed that you can build, if the splice diagram has the edge determinant and semigroup conditions, then you can get a universal abelian cover of it that is of splice type. And they conjecture that these universal abelian covers of rational or rational homology sphere, minimal elliptic, and non-cuspidal surface singularities are of splice type. And that was proven by Okuma. So there's a long history of these splice diagrams, but I think that the main players for us today are going to be the series of results by Neumann and Wall, and this was really the inspiration for us to start our work. As I was mentioning, in the coprime setting, they have a very nice conjecture describing the topology of the Milnor fibers of these systems. And our aim from the beginning was to try to prove this conjecture. It took us a little bit of time, and many different pieces have to come together. One of it is a tropical setting, and then we're going to have some log geometry component, but that, again, that's what Patrick discussed back in September. Okay, so I mentioned that there's going to be some complete intersections, and the question is now how to build these systems of equations. And as I said, the semigroup condition is really the key here. And so the idea is going to be inspired by what happens in the Briscoe setting. So maybe let me discuss this first. So what you're going to do is you're going to look at the leaves of your graph, and these are going to be associated to variables of your system. So I'm going to have a Z1, Z2, all the way up to Zn in this case. And if I want to get a complete intersection that describes a surface, I really need to have n-2 equations. And so the easiest way to build equations out of this is to look at the weights surrounding my node V and use them as exponents of these variables. So you're going to have n-2 equations that are going to have the same support. So these are going to be my monomials are all going to be the same, and they're going to be the variable associated to the leaf raised to the power the weight around V in the direction of that leaf. And then I have the freedom, excuse me, I have the freedom to choose my coefficients. These are going to be complex numbers. and they're going to form n minus 2 by n matrix. And what we call the Fan-Brieskorn-Hahn condition says, if you want your singularity to be isolated, you need to impose that the maximal minors, all maximal minors of this matrix have to be non-zero. If that's the situation, you're going to get an isolated complete intersection surface singularity. So the idea of these splice-type systems developed by, as I mentioned, Neumann and Wall, is basically do the same construction. So you're going to have the same number, the variables are going to be encoded by leaves. And then I'm going to have, for each node in my graph, I'm going to have a number of equations. How many valency minus 2? And if you add the number of equations, you're summing over the nodes of your graph. And in the end, you get the total number of leaves minus 2. So that's going to be lead to the expected dimension 2, namely a surface. So let's do, before we do the general case, let me just go back to the running example that we had and see what kind of systems can we get. And as I mentioned earlier, we have two systems because we're going to have two ways of writing 11 as a combination of 3 and 2. Okay, so let's see the situation here. So as I mentioned, we had these numbers 2 and 5. So 2 was the linking number of u, sorry, not the linking number, but a factor of the linking number joining u and 3. So it was 2 times 3 times 2, and this is the 2 that encodes that 2. And similarly, for the other factor, we have a 5, and that comes precisely from that 5. And so in the case where I had, in the Brieskorn case, I would just take the weight to be the exponent of my variable. So now what I'm going to do is I'm going to use those scalars as the exponents of the corresponding variable. So in the first situation, I'm going to have one equation coming from my node u, because I have valency 3. And the equation, in this case, I'm going to choose coefficients to be 1. And so I have, in the first situation, I have the node u, and I have only one way of having a power for z1, and that's just considering that exponent 2. Then the second situation, I have z2 to the cube. And then, as I said, going in the direction of the internal edge of my graph, I have 2 leaves. And how do I pick the monomial? Well, I have to look at these 2 scalars, and that's going to be what gives me the exponents for each of the leaves. Okay, so that's going to be the first equation. The second system, I'm just going to copy the second. It's going to be, I have one option for the equation. But then in the second situation, for the 11, that's going to give me one monomial for v in the direction of u, and I have 2 options for doing so. So in the first situation, let me pick the first option. So the 3 here came from the linking number of v and lambda 1. So that was that 3 over there. And so if I have to write down the monomial, there's going to be z1 raised to the power 1. And then the z2 is going to be raised to the power 4. And then for the other 2 leaves, I have no choice. So I'm going to choose z3 to the power 5 and z4 to the power 2. And that's going to be one type of system. And then, of course, the second way of writing 11 will give me the second possible system. So I'm going to get now z1 is going to be raised to the power 3. Z2 is going to be raised to the power 1, and then I have Z3 to the 5 and Z4 to the 2 as before. So those are going to be my 2 type of systems. Of course, you might wonder, well, every splice, I'm going to build one splice system. I have to make a choice. And so, we'll talk a little bit later about what happens if I choose one monomial instead of the other in various contexts. Okay, so now let's do the general case. So as I mentioned, these splice type systems of Neumann and Wall are going to follow the same construction as the Brieskorn systems. So for every node in my graph, I'm going to consider now the the subtrees that are obtained by moving from V in each of the directions of the edges that I have. S in this case here is the valency of my vertex of my node V. And the statement is going to be each edge or each subtree is going to give me precisely at least one monomial to consider. And the monomial arises from the semigroup condition as before. So the fact that I can write the dV as in the semigroup obtained from the linking numbers of V with each one of the leaves is going to give me at least one monomial in the variables arising from those leaves. So these are the terms of my equations. So I'm going to pick exactly the same monomials. And then, of course, as before, I have valency -2 equations, and I have the freedom to choose my coefficients. And so in order to get, again, a complete intersection, I would like to impose the same boundary-scarn-Ham type condition, namely all maximal minors of these matrices have to be non-zero. So technically speaking, this is what Neumann and Wohl call strictly splice type. So I'm just going to have monomials. And now, as I mentioned earlier, sometimes you have choices of monomials. So these are called admissible monomials. Sometimes you have a choice of more than one admissible monomial to choose from. And the question is, well, which one should I pick? And if I pick two different ones, do I get the same kind of topology? So that's kind of a delicate matter. So in the case where your splice diagram was coprime, you can free yourself from independence of choices if you're willing to allow some higher order terms in your equations that are leading to convergent power series near the origin. And that's because you're going to be able to deform one singularity to the other if you allow the tails. Now, if you drop the coprime condition, then the tails have to be equivariant with respect to some group action. And in fact, we have some example where if you don't have equivariant condition, then you won't get singularities that can be deformed one into the other. So this is a delicate matter. Now, as I mentioned, there's some potential group action, and if you want to say your tails have to be your higher order, well, higher order with respect to what weight? And so the weight vectors that I'm going to pick are going to be associated to each of the nodes. So the equations for the node V are going to be weighted with respect to a specific weight vector, and that weight vector is going to be its coordinates are going to be the linking numbers of your node V with every single leaf on your graph. So this is going to be a positive integer weight. And with respect to that weight, the tails are going to have higher order. And we're going to see in a minute that the weight for each one of these is going to be dV. So higher order really means weight larger than dV. And so the splice type systems that we are interested in are going to allow tails that have to be have higher order with respect to this weight. But there's the only condition we're going to impose. And the reason behind this is because when we do study the combinatorics of these graphs and their tropicalization, there's no need to impose any extra conditions on the tails. So that's basically what allows us to be a little bit more relaxed in our assumptions on the tails. Okay. So let's go to, again, back to our example, just to see what happens with these weights for each one of the nodes. So the first weight is going to be this WU associated to this node, and we have to consider linking numbers of U with respect to each one of the four leaves. So the first one is the node U and the leaf lambda 1, and so here I have 7 times 3. Which is 21. Then the second one is going to be now 2 times 7. So that's going to be 14. The third one now is going to be the linking number between U and lambda 3. So I have to take the product of 2 and 3 with 2. So that's going to give me 12. And finally, for the last pair, I have to consider 2 times 3 times 5. And that's going to give me 30. And similarly for the other weight, we're going to have 30 coming from 2 times 3 times 3. The second linking number gives me 2 times 5 times 2, so that's 20. And then for V and lambda 3, I get 11 times 2, which is 22. And finally, I get 11 times 5, and this is my 55. So these are the two weight vectors that I have to consider. And let me pick one of the two possible systems that I mentioned earlier, and let's compute the W weight and the WV weight for each one of these equations. So this was the equation coming from the node U, and the second one was the equation coming from the node B. And so in this case, we have the way to compute the weight here is the weight with respect to the first variable is 21. 21 times 2 gives me 42. Second, I have the weight for Z3 is 14. And then 14 times 3 is again 42. And then finally, Z3 times Z4 gives me 12 plus 30 as the weight. And that's again 42. And if you remember, this was exactly the weight, the du quantity that we defined. And in this case, you see that all the monomials have the same weight. Now, if I consider the weight coming from the other node, in this case, I will get 30 times 2, which is 60. Then the second one is going to give me now 20 times 3, which is again 60. And then finally, the third one is going to give me 22 plus 55, which is larger, 77. So in this case, the overall weight of my polynomial is going to be 60, and that's precisely the linking number between U and B. And similarly, in the other case, we're going to have, let me compute the lambda WU and UV weights. So in the first situation, I'm going to have 21 plus 4 times 14. So I'm going to get, so in this case, I'm going to get, let's see, so 21 plus 4 times 14. Then in the second situation, I'm going to have 5 times 12, which is 60. And then in this situation, I have 2 times 30, which is again 60. And 60 beats this other weight. And again, this is precisely the linking number of U and B. And if you consider the second weight vector, the one associated to the same node, then in this case, we're going to get all the monomials are going to have the same weight, namely 110. And this again is the quantity dV that we were mentioning. So in this example, you can see that the systems are really quasi-homogeneous with respect to the weight associated to the equation you're looking at. And if you're looking at other weights, what's going to happen is you're going to lose precisely one monomial out of the total that you had. Okay. So these are going to give you by systems that are quasi-homogeneous with respect to these weight vectors. So one of the main theorems of the series of papers by Norman and Wall says if your splice diagram satisfies this edge determinant and semigroup condition, you can show that the splice type systems with the tails included determine an isolated complete intersection surface singularity. And the way they proved this was really, when I was learning this for the first time, I found this kind of computations really remarkable. So the first thing they do is to check that the dimension is 2, is really they look at the system and they impose vanishing of 2 extra variables. And then they check that the variety defined by these, or the germ defined by these objects, is just the origin. So that will ensure that the dimension is at least, well, it's at most 2 in the original setting. And if because we had the right number of equations, we get dimension 2 and a complete intersection. And then to check that this is really an isolated surface singularity, they really go ahead and compute the resolution of the whole system by means of weighted blowups. And the weighted blowups are associated to precisely these weight vectors that we were looking at earlier. So they have, for each node, you're going to get a cyclic quotient singularity. You do the resolution, you get the typical star shape resolution diagrams, and then you have to patch things together And you will get resolution graphs that are basically a shadow of the splice diagrams you started with. And then you conclude from here that not only that the singularity is isolated, but you can really realize these weights as divisor evaluations arising from your exceptional divisors evaluated at the coordinates of your ambient Cn. So it's really a lot of work, and they do it in great detail. So it's just really remarkable. Okay, so far I've told you the foundations of what are these splice diagrams, where they arise. And now let me tell you what are our main results, and then we'll talk a little bit about the proofs or the ingredients, the combinatorial ingredients that arise, or that we need to prove these results. So again, as I mentioned, all these statements are joint with Patrick Popescu-Pampu and Dimitri Stepanov. So our first theorem gives an elementary combinatorial proof of this statement by Neumann and Wall, namely that these splice type systems are going to give me isolated complete intersection surface singularities. And the proof is, again, elementary, depends on the eyes of the beholder. I'm a combinatorialist by training, so for me, these calculations are simpler to understand than the resolutions by weighted blowups. But in the spirit, they're very, they resemble the same, although the techniques are easier from my perspective for our proof. Then the second result that we are able to get is that these systems are very nice because they describe Newton non-degenerate complete intersections in the spirit of Khovansky. So what that means in this case is our equations coming from the nodes, and I have valency -2 equations for each node. They form a regular sequence in the convergent power series ring. And then for each positive weight vector in the positive orthant, then you can take the initial forms of these nodes. These are, as I mentioned, the monomials that have minimal weight with respect to these minimal value with respect to these weights. And these define a normal crossing divisor in a neighborhood of the intersection of these initial forms, but viewed inside the torus. So an equivalent condition for this second part is going to be that if you look at the gradients of each one of these initial forms, these are going to be linearly independent at every point in the intersection. So that's an equivalent condition. And this result is nice because there are not that many known examples of systems that are Newton non-degenerate complete intersections. So this adds a large class of families to know. If you want to study this topic and try to come up with conjectures, this is a nice family of test cases to check. And, okay, and then the third thing that we can get out of this is it's part of the way we prove this theorem of Neumann and Wall is we're gonna use these weight vectors to embed our splice diagram inside a standard simplex. They're gonna, if you have a graph with 4 leaves, you're gonna embed it you're gonna have a tetrahedron sitting in 4 space, and we're gonna consider the fan over that. So that's gonna be a simplicial fan by construction. And once you have a fan, you can construct a toric variety. So this is an X sub F lambda. And I'm going to have a birational map that goes from this toric variety to Cn. Cn I think of as the toric variety associated to the fan that is just a positive octant. And this birational map, when I restrict the target to the vanishing of my splice type system, we get a modification of it, and the strict transform of this splice type system is going to have a nice property, namely, if you consider the strict transform together with the pair consisting of the strict transform with the intersection of the strict transform with the boundary of my toric variety, that's going to be a divisor, and this pair is going to be a toroidal pair. So if you look at it locally, it really looks like a toric variety together with its toric boundary. And the advantage of that is that then you can, once you're in the setting, you can focus on your strict transform and you can resolve any singularities you have just by toric modification. And so this theorem that we write down here extend results that were recently proven by De Felipe, González, Perez, and Murtada. And their result says any germ of a plane curve singularity can be resolved by one toric modification after re-embedding the ambient smooth germ, in our case C2, in some ambient Cn. And so this was for any plane curve singularity, the irreducible setting, a reducible case was proven in 1997 by Goldin and Tessier. So this goes back to, again, the famous Tessier question of can you actually resolve singularities by means of toric modifications. After, of course, you re-embed, and once you re-embed, you can really just focus on toric geometry. And as you can see, of course, the Theorem 2 is stronger than Theorem 3. Yeah, so that's basically Theorem 3 is going to be a corollary of Theorem 2. Okay, so as I mentioned, the title had local tropicalizations. I mentioned Theorem 1 has tropical geometry as a key component of its proof. I'm aware the audience is not really coming from that world, or many people in the audience, so I'm going to try to give you an overview of what this tropical geometry can do for you in the case of singularities. Okay. I don't know if I'm supposed to ask for questions, or maybe I should wait for questions at the end. I'll try to leave time at the end for answering questions. Okay, so before I do that, let me just go back to our example and at least see what the ingredients of the proof are going to be. So we had this splice diagram, we had the system, and I would like to embed this splice diagram inside the tetrahedron, as I mentioned. Excuse me. And I do this by just looking at nodes and leaves of my graph, and I have to give a point on the tetrahedron. So for leaves, the easiest thing to do is to send it to the standard basis elements. These are going to be the vertices of my tetrahedron. And then for the nodes, I have my weight vectors, WV, and if I want to put them in the tetrahedron, I have to normalize it. So I'm going to divide by the one norm of my weight vector. And then I'm going to extend on the edges by looking at convex combinations between the images of the corresponding vertices. So that's going to give me, here you can see the picture, how you can embed this standard splice diagram in the tetrahedron. And one nice thing about this is that because of the construction, there's a lot of very rich convexity properties. So one of the properties that you're going to see is that this edge joining U and V is really going to be in the segment joining the barycenter of all the vertices on this side of the tetrahedron and all the vertices of the other side. So this U and V are going to be in the segment joining the barycenter of one face with the barycenter of the complementary face of the tetrahedron. So there's a lot of barycentric calculus involved in this. And as I mentioned, the map is well defined, but it's not clear at all that this map is injective, right? So, and this is really important if we want to build out a fan out of this. I really want this map to be injective, so that if I take the cone, there's also no issues with faces intersecting or cones intersecting along something that is not a common face. And this is really, the way we showed this result is by means of an inductive procedure. And again, the rigidity of the combinatorics here comes into play, because what we're going to consider is basically we're going to start chopping a tree along nodes. And what's going to happen is if you consider certain subtrees, which we're going to call star full, because any node is going to, the star around each node is going to be forced to be inside your tree. If you do that, then, for example, in this case, the U, the E3, and the E4 are going to form, again, a simplex. In this case, it's a two-dimensional simplex. And the node that we had is going to be in the interior of the simplex. So you're going to do a construction from the outside inwards in a sort of inductive fashion. And that's going to allow us to prove injectivity and other things as well. Then if we want to compute actually what the initial forms are, in this case, we will have to consider two types of weights. So one is going to be the weights coming from points on the graph, in the relative interior of my simplex. And then I'm going to have weights in the complement of the graph. And what's going to happen is, if it's in the complement of the graph, then we're going to be able to find one node so that if you look at the initial forms for these equations, their linear span is going to contain a monomial. So there's going to be really no intersection in the torus. And so that's one of the things that allows us to ignore these guys for the purposes of the Newton non-degenerate condition, because intersection is empty. Now, if you look at the weights coming from the graph, then basically we're going to have to analyze two types of weights. One that are in the interior of edges. So in this case, I have 5 edges. And then on the other hand, I'm going to have to consider weights coming from the nodes of my graph. And one thing we show is that in all these 7 cases, this initial forms for in this case, we have these 2. These are going to form a regular sequence in the convergence power series ring. And this is going to part of the key results that we're going to need is a lemma that was the proof was graciously provided to us by Jonathan Wall, and that's the appendix to our paper contains this kind of result. So let me show you the example. So the beauty of this calculation now is, in this case, we had 2 equations, and we have, as I mentioned, we have 7 types of weights to consider. We have the weights coming from the vertex, the 2 relevant nodes in my graph, and then I'm going to have weights associated to the edges. And if you look at the combinatorics of the problem, so we're going to have, again, the graph is here. We're considering the weights coming from this node. If you just look at the weights, the weight vector associated to the node as well, all the monomials survive. Whereas if you look, for example, on the second line, you're going to have the same equation, and now you're going to look at weights coming from the node lambda, the vertex lambda 1 and the node lambda 2. And this is going to, if you consider these 2 weights, you're going to drop the monomial going in that direction. And the only 2 that survive are the one for lambda 2 and the other admissible monomial. So in this case, you see that. Similarly, now, if you look at the weight coming from U and lambda 2, you're going to lose this one admissible monomial, and that's why you get these binomials. And in the third, the remaining 4 ones, you're going to have the monomials, the equations at U, and then you're going to consider either combinations of vertices and of the graph in this side of the graph, and you're going to drop then the monomial going in that direction, and so on. And so similarly, a similar situation will come from the second equation, and all there's essentially, we get, as you see here, we get 4 types of initial forms depending on which weights we're considering. And this is going to be very helpful for us for actually computing this, checking this Newton non-degeneracy condition. Okay, so let's go to, again, the main technique. And so the main technique is going to be local tropicalization. So this is a theory that was developed by my co-authors in 2013. And the slogan, or the aim, as far as I understand, is that this, there's a version of tropical geometry for subvarieties of toric varieties or subvarieties of tori, algebraic tori, and this local tropicalization is a version of tropical geometry in the local setting. And the original motivation was to try to use this construction to study singularities. So the first paper developed the whole theory, and so now we're sort of applying these results for concrete singularities. So the setting is I'm going to have a germ of a singularity inside Cn, and it's defined by an ideal in the convergent power series ring. And so I'm going to have two types of tropicalizations, the positive tropicalization and the non-negative one. And the positive one says, well, you just consider weights that are in the positive orthant. And the condition is that the initial ideal, that is the ideal generated by all initial forms in your ideal, has to contain no monomial. So the no monomial is allowed here. In other words, when you compute the variety here inside the torus, you will get a non-zero, it's non-empty, right? And the non-negative one is the same, except that I'm allowed to have some zero coordinates among my weights. So the key example you should have in mind, if you've seen this global tropicalization, the global tropicalization is the same, except that we work with a polynomial series ring or with a Laurent polynomial series ring. And so if your germ is really generated by polynomials, then your local tropicalization is obtained by looking at the global tropicalization in the torus and intersecting with the positive orthant. So you're restricting your global tropicalization to the positive cone. So there's a bunch of results that are true for global tropicalizations that if you think about this key example, they descend to the local tropicalization naturally. One is the local version of the so-called Beery-Groves theorem that says if you have a variety or a germ defined of dimension n, the tropicalization in this case is going to be a fan inside this positive orthant, and the dimension is going to be preserved. So that's one feature. We can see the dimension of our germ in the tropicalization, and that's one of the things that we're going to use to check that the splice type systems really have dimension too. Now, if your germ is equidimensional, so all components have the same dimension, then the positive tropicalization is can be equipped with weights on the top dimensional cells. All top dimensional cells have the same dimension, and you're going to obtain what we call a balanced fan along these codimension one faces. So if you were thinking about a curve, you will have the codimension one face that's going to be a node, and then you're going to have pictures like this. So in this case, if you imagine the directions as being 1, 1, 0, -1, and -1, 0, you sum the primitive directions, and then you get 0. So that's sort of the higher dimensional version is an analog of this setting. So in the hypersurface case, so if you have a germ defined by just one power series F, then the tropicalization is just a codimension 1 skeleton of the Newton fan of F. So let's see a picture of this. So the E8 singularity, the equation was Z1 squared, Z2 cubed, plus Z3 to the 5 is equal to 0. The resolution diagram is the known E8 thinking diagram, and the splice diagram in this case has weights 2, 3, and 5. The Newton polyhedron is written there, so I have the 3 monomials, and then I have to add copies of the positive octant. And in this case, the 2 skeleton of the Newton fan has, I color-coded the vectors by duality. And so you see in this case, the local tropicalization is going to be the union of these 3 two-dimensional cones. And they look combinatorially. If you slice this with a 2-dimensional simplex, you're going to get the splice diagram. And that's really the way that we're going to embed the splice diagram inside R3 and get the tropicalization out of that. So what does the local tropicalization know about my germ? So there's a local version of, again, a known theorem by Develev that basically says if you want to build compactifications of a subvariety of a torus, you should take the toric variety associated to the tropical fan. So that's going to be a partial compactification because it's not going to have the dimension n. But the point is that partial compactification doesn't miss any points in the closure. And so in general, that's basically the slogan. And so if you want to, you have a toric variety associated to a fan, and then you have the associated toric morphism defined by this fan. You consider the strict transform of your germ and the restriction of the corresponding toric morphism. Then your restriction map is proper if and only if your fan contains the tropicalization, the support of the fan contains the support of the tropicalization. And if that inclusion holds, then you get really equality if and only if, when you look at the toric boundary of your strict transform, intersected those points in the torus orbits in the boundary have the meet in the expected codimension. And that's the codimension is really going to be the dimension of your associated cone and your input fan. Okay, and so then the tropicalizing fan basically is going to be a fan that is supported on the local tropicalization, and it can be refined so that the initial forms are constant along each cone of your fan. Concentrated. The theorem is that the tropicalization span always exists, and we have, if you want to look about with in the compact setting, you will have to look at not just non-negative tropicalizations, but you need an extended version that considers toric boundary strata.
Let's try.
And
Angelica, can I ask you to conclude?
Yes. Yeah. And so the theorem is that the cone over the embedded splice diagram is a tropicalizing fan for this splice diagram. Yeah. And using this, really, we prove all these results. Okay, so sorry for going a little bit over time, I think. So thank you for your attention.
Okay, thank you very much for this nice talk. So there is, a little bit of time, so for a few questions.
Thank you. Hi. So I have a question about when you are using the semigroup condition, then you can obtain different equations from different factorization in the semigroup.
Yep.
But can you always find a system of weight where the degrees are essentially the same at reordination? Because in this example, the equations are different, but you have a system of weights where the weights are the same in both cases. So is this casual or is this?
I'm picking the same weights because this one had another option. I think if I remember correctly, let's see. I think it was Z1. It was 3 and 1, something like this. If no matter what admissible monomial you choose, the weights are going to be the same. So the weights here, as I mentioned, part of the results of Neumann and Walsh say these weights are really coming from divisory evaluations associated to the resolution. And so these weights are really, they have some geometric reasoning for picking these.
Yeah, and just one more comment is just because in the W there is the same that the WB in the other equation. So is this a special weight that you can always take, or is this just?
Yeah, the weights really come from the splice diagram. So here we have, our system had 2 equations, and I was just trying to show you what happens with the weights if you look at each one of the equations of your system. So what happens in general is you're either going to be homogeneous or you're going to lose exactly one monomial after when you consider initial forms. And the weights are really coming from the splice type. I'm just considering these set of weights. I'm looking at every single equation in my system and computing the initial forms with respect to these weights.
Okay, thank you.
You're welcome.
Okay, maybe time for last question. Okay, no other questions, so your talk was clear. So let's thank Maria Angelica again.
Thank you.